Hi there. So we are moving on to Unit 8, which is all about acids and bases. And so we've already done a little previews of acids and bases. And actually the first couple videos here are going to be word for word, what we went through in class way back in Unit 4. So this is really a review if there's things that are unclear or things that you want a refresher on. But all of these, we've actually taken these exact same notes, like copy and pasted a few months ago. So in this unit, we introduced the idea of acids and bases, but really it's hard to have gone through units 4, 5, and 6 without knowing anything about acids and bases. So a lot of this information is going to be repeated. So there's a few different definitions of acids and bases. The first definition is really the narrowest. It's the one that there are the least examples of. And those are Arrhenius acids and Arrhenius bases. So Arrhenius acids are our strong acids. These fully dissociate in water. And those are HCl, HBr, HI, and they're right in line on the periodic table. Then HNO3 and H2SO4, and those are common, probably the two most common polyatomic ions. And then there's HClO3 and HClO4. That HClO3, some books will say is not strong, so don't worry, it won't be an issue. The strong bases, or Arrhenius bases, again, fully dissociate to produce OH minus or increase the OH minus concentration. And so those are the hydroxides of the alkali metals and the alkaline earth metals starting with calcium. So lithium, sodium, potassium, rubidium, cesium, and then calcium hydroxide is CaOH2 because calcium is 2+. And then SrOH2, strontium hydroxide, and barium hydroxide. So you need to know those, and hopefully you've learned those from previous chapters. And then this graphic here just helps us to look at, just a reminder is, what do I mean by fully dissociate? So when we talk about a strong acid, HCl, there are 0 molecules of HCl in HCl aqueous. The only time that you actually find the hydrogen bonded with chlorine is in gaseous hydrochloric acid. And then actually we don't usually call it hydrochloric acid. We call it more by its ionic name of hydrogen chloride. When a weak acid, though, only partially dissociates, which means that we get to introduce the equilibrium symbol, right? And as opposed to the full arrow symbol with strong acids and strong bases. And you can see that most of the time, the weak acid is actually together. That covalent bond is still intact, whereas in a strong acid, it always breaks. And this picture here shows us magnesium hydroxide. So this is a weak base, and you can see that it is, together here, and HCl. And then those two react. So acids and bases react so that the OH of the base and the H of the acid come together to form water. So in an acid-base neutralization, water is always a product, and the other product is an ionic compound. So in this case, magnesium chloride. And you can see, sort of interesting here, how magnesium hydroxide is not very soluble in water, and then we make magnesium chloride, which is quite soluble in water. And then the second section of this chapter talks about the second definition of acids and bases, which is as Bronsted-Lowry acids and bases. So we have redefined our definition of acids and bases for a few reasons. The first one is that there were many compounds that were considered bases. They turned litmus paper blue. They tasted bitter. You could measure their pH and it was above 7, but they didn't dissociate to produce OH minus. they did increase the OH minus in solution. That's why they act as bases. But they didn't quite do it the same way that the Arrhenius bases definition worked. So what we have sort of concluded is that a better definition is that in acid-base reactions, there is a transfer of the hydrogen ion, and that the acid is the hydrogen ion donor and the base is the hydrogen ion acceptor. So first of all, when we talk about hydrogen ions, we will often call it a proton. Those two words can really be used interchangeably. And that's because hydrogen is only a proton with one electron around it. There's no neutrons in hydrogen. So therefore, if it's H+, which means it's lost an electron, it really is just a proton. And that hydrogen ion really doesn't exist just floating around in water. So a more accurate way to represent it is actually this thing that we call the hydronium ion, or H3O+, just showing it complexing or, getting together, making a covalent bond with water. So H3O+. And we're going to use H+, hydronium, proton. Those are really interchangeable. So again, there's the definition of a Bronsted-Lowry acid and a Bronsted-Lowry base, proton donor and proton acceptor. And you can see in this case we have HCl, which could be considered an Arrhenius acid, but also Bronsted-Lowry acid, because in this reaction, it gives the hydrogen ion to water. And that is the first time that we're going to see water as labeled as a base, which is strange because we think of water as being neutral. And that becomes even more strange when we start looking at the balanced chemical equation for ammonia in water. So ammonia is the chemical compound NH3. This was what was known since ancient times as a base, but it doesn't even have OH minus. So how can it dissociate to produce OH minus? Well, it doesn't, but it does react with water. And it's weak, so we got that equilibrium symbol in there. Water actually donates the hydrogen to NH3. NH3 is a base, it is a proton acceptor. So on the product side, we see it as the ammonium polyatomic ion, NH4+, and OH minus. Remember, from baby chem, we often wrote water as HOH to just remember that hydrogen can break off and leave behind OH minus. So then it seems to this makes sense. Why, right? Why ammonia can be considered a base, because it does produce OH minus when it reacts with water. So that's why it tastes bitter and it's, it turns litmus paper blue and it's got a pH greater than 7. So then that brings us to, well, wait a second, in this reaction, water has really acted as an acid, and in the previous reaction, water acted as a base. That doesn't make sense. Water is neutral. Well, actually, water is amphoteric. Another way to put that is amphiprotic. They mean the exact same thing. They mean they can act as either an acid or a base. They can kind of go either way. So there's some compounds that can do this. Ammonia is water is the best example of this. But another example of this will be a category of compounds that this is definitely a silly thing that I came up with a while ago, calling them papas, because the actual word for it is, or the actual term for it is very long. The protonated anions of polyprotic acids. So a polyprotic acid, just as a reminder, is an acid with more than one ionizable hydrogen. So H3PO4 is phosphoric acid, and it can lose 3 phosphorus. After it loses it can lose 3 hydrogen ions. So after it loses its first hydrogen ion, we have H2PO4. So H2PO4 is think of the words, protonated, it has a hydrogen, anion, it is a negative charge of a polyprotic acid. So H2PO4 negative could gain a hydrogen and reform phosphoric acid, or it could lose another hydrogen and become So HPO4 2- is also a papa, because it could gain a hydrogen and become H2PO4 negative, or it could lose another hydrogen just to become the phosphate ion. So these guys will often be used as examples of polyprotic, they'll be used as examples of amphoteric substances. And then we get to the concept of Bronsted-Lowry acids and bases and this conjugate acid, conjugate base. Because when we talk about Bronsted-Lowry, we often talk about the reactions. We use this with weak acids and weak bases, which we have learned means that that's an equilibrium reversible reaction because they don't fully dissociate. So an acid, after it loses its hydrogen ion, is considered its conjugate base. Likewise, a base, after it gains the hydron, is considered a conjugate acid because these reactions are reversible and they are in equilibrium. So HNO2 is a weak acid, right? HNO3 is strong, but HNO2 with the nitrite ion is weak. It will donate a proton to water. So water is considered the base here. When it forms, right, the acid, after it loses its hydrogen, becomes what we call the conjugate base. Because look at the reverse reaction. In the reverse reaction, NO2 negative nitrite acts as a base because it accepts the hydrogen back from H3O plus. And in the ammonia reaction below, you can see NH3 is a base. It accepts the hydrogen from water. But the reverse reaction, the ammonium ion is a conjugate acid, right? It will donate the hydrogen back to water. So how, acid base, you might be asked to identify the conjugate acid base pair. And if you're asked to identify those, they always differ by only a hydrogen ion, right? Look at how these guys differ. They only differ by one hydrogen ion. The same way for the other pair there with water and the hydronium ion or water and the hydroxide ion. They only differ by a hydrogen. An acid becomes a conjugate base, a base becomes a conjugate acid. And we do always label the conjugates on the right and the acid bases on the left. So here we have some sample exercises here. As always with these exercises, if you feel like I want to give this a shot on my own, give it a shot. Try these on your own and then play the video again and see if you get them right. Or if you want to follow along, you can follow along. Maybe do the first one together and then pause and do the second one. So the first question says, what is the conjugate base of these guys? So first of all, if I look at them, if you're asking for the conjugate base, that means these are all acids. So HClO4, right? How could this guy differ? So we're looking at the conjugate base is this guy minus its hydrogen because this would be the acid, so it'll be donating its hydrogen. So this would be ClO4 negative, the perchlorate ion. H2S, right? This guy would donate a hydrogen, so this would be HS negative. So you also have to keep track of the charges, right? If it loses a positive, it will become negative. We get PH4 plus. It loses a hydrogen and loses its positive charge, so that's PH3. And HCO3 negative, it loses its hydrogen and it becomes more negative. So that's the carbonate ion, CO3 2 minus. And then what is the conjugate acid of these guys? Well, that means that they're bases. So the conjugate acid is this plus an H plus. What does it become after it gains an H plus? The cyanide ion becomes HCN. SO4 2 minus becomes H, SO4 negative. H2O, after it gains a hydrogen, becomes H3O plus, and HCO3 negative becomes H2CO3. And this is another great example, right? Here it's acting as both an acid and a base.